All right, sorry about that. I forgot to actually get the StatCrunch screen up, but I thought I would write this stuff down anyway. This is a summary right here of this situation. Remembering that the standard deviation of our sample means is going to be the population standard deviation divided by the square root of the sample size. But the means, the averages, are going to be exactly the same. In this situation, the pennies, we've got a 2.46 mean and a 0.02 standard deviation. With one penny, the weight being greater than 2.465, that's just using the population values for the mean and standard deviation. We're looking for the the probability of that penny being greater than this. But in the second part, we're looking for 10 pennies. And if you can make a prediction about this, is the probability of a single penny weighing more than a higher value, the single penny going to have a higher probability than a group of 10? What do you think? And here, you could pause it right there if you wanted to think about that, or talk to the person next to you as long as you're more than 6 feet from them. Here are the two values in StatCrunch. In this case, with our standard deviation of 0.02, here with our standard deviation of 0.0063. That is the 0.02 divided down by the square root of 10. And I don't know if you can read the numbers, but maybe you can see the size of the red values. The probability of a single penny weighing 5 thousandths more than average is 40%. But the average of 10 pennies weighing that much more is about half that, down to 21%. It's a much less likely occurrence to have that group of pennies weighing more than average. Right? So that is the idea of how that works. And remember, for StatCrunch, if you need help with that, feel free to send me an email on how the StatCrunch works. Okay. Where do I get back to? There we go. If we did this again with the same situation, what about at least 2.473? Not 2.465, but 2.473. And 10 pennies weighing more than 2.473. Well, we could easily go right back to StatCrunch and there it is. We could easily go back to StatCrunch and put values of 2.473 and compute 2.473 and compute. Wow, look at that. A single penny has a 25% chance of weighing that much, but a group of 10 pennies, you're down to less than 2%. Less than a 2% chance that this group of 10 pennies is going to have an average weight of that much. And it's really not that much more. 2.46 is the average. 2.473, it's only 13 thousandths more. But again, to have a group like that to weigh that much is just not very likely at all. Okay, so now, yep, we're good. Now, this is a fun thing. Objective 2 for this. What happens now? The pennies were normally distributed. Toddlers normally distributed, right? So if we're taking a sample of these things, well, a bunch of samples taken from a normal population is probably going to be normal, right? Well, what if we take a bunch of samples from a population that is not normal? We take a bunch of samples from something, and not every situation is normal, right? But we're not studying the population as individuals. We're studying the population as samples. And does that make a difference? And we're going to find out that it does. Remember a fair die, 6-sided number cube dice. If we take one of those and roll it, what are we going to get? Well, either 1, 2, 3, 4, 5, 6. Is any one of those more likely than the other? No, they're all equally likely. So if I were to do a roll this die 6,000 times, would we expect to get roughly 1,000 of each of these? Yeah, not exactly 1,000 of each of these, but roughly 1,000 of each of these. Does this look more normal or does this look more uniform? Actually, this is a very great example of a uniform distribution. But what if instead of rolling just one, what if I took 4 dice and rolled them all and then averaged what I saw? Maybe I got a 1, 2, 3, 4. And I add 1 plus 2 plus 3 plus 4 and get 10. Divided by 4 is 2.5. The average for that would be 2.5. And I did that a whole bunch of times, right? I did that 200 times, and I listed all of the averages. What might those averages look like? Or what if instead of just 4 dice, I took 10 dice and just dumped them on the table and added all those together and divided by 10? What would I probably get? Or what if I did this with 30 dice, just dumped a whole bucket of dice on the table, added them all up, divided by 30? What do you think the average would be? Well, I did this, not with dice though, but with an Excel spreadsheet, because that's what we do. We like Excel. Let me show you this. Spreadsheet if I can find it. Here it is. This right here, before I show you the data with graphs, this is 200 different trials, right? And this is 1 dice, and if you can see these numbers, this is a 5, a 2, a 2, a 4, a 1, a 4, because the code is just pick a random number between 1 and 6. Well, this 4 right here takes the random between 1 and 6, another random 1 and 6, another random, adds them together, divides by 4. And this is 10, and this is 30. And what I then did is graph these. And every time I press F9, I can see how those look. So this is a different one. This first graph is just with the single die. And you can see that it's fairly uniform. Some are a little bit more uniform than others. Sometimes there are some pretty high ones. Look at that. That's very nice and uniform throughout. Well, what does a graph look like for size n equals 4? In this case, we can see that, well, there are a whole lot more towards the middle. And does that make sense? That I'm probably not going to get a whole bunch of low numbers when I roll 4 dice, right? Though in this case right here, there were actually 2 times that I must have rolled 4 6s, because the average was between, well, on the very high side. And every time I recalculate, I can make a new little graph. Wow, we had a whole bunch of, there are a couple of maybe 4 1s, and here were 4 6s. But again, most things in the middle. Does it kind of start to look a little normal, right? What about the sample size of n equals 10? Look at that. Look, there are almost no outlying numbers. In fact, I don't think I've ever gotten 10 1s. We've got 1 that's way down there. That must have been a whole bunch of 1s and maybe a 2 or a 3 or something. But again, where are most of these averages? They're right around this value here, between 3.3 and 3.7. About 3.5. What if I keep scrolling down for a size of 30? There's just no outliers in there at all. That looks just beautifully normal. And what does that mean? Well, I'll show you what that means. Yep, look at that, pretty cool. So what does this mean? Well, it means no matter what the sampling size, the mean of the sample distribution is equal to the mean of the parent. Every time, the average of the sample is going to be the average of the parent. The average dice roll, every time you roll a dice, the average dice roll is 3.5, right? But the standard deviation of the sampling distribution is going to be divided by that out. And the central limit theorem, that's a vocab term you might see in your book as well. The central limit theorem states that the shape of the distribution of the sample mean, that's what we've been doing in this whole section, becomes more and more normal. Even if it starts out completely uniform, it will become more and more normal as time as time goes by, as the sample size increases. If the population is normal, it doesn't matter the sample size you use. But if it's not normalcy, or its normalcy is unknown, if you have a sample size of 30 or greater, that is going to be sufficient. That's what the people in that big gray building in Washington, D.C. decided. That 30 is, you might see another stats book that uses 20 or 40 or 50 or whatever, but this stats book says that 30 is going to be sufficient to result in a normal sample distribution of the sample mean. And then to compute probabilities, well, since we know how to do this, we know how to find those values like I did with StatCrunch just a little bit ago. All we have to do then is recognize, okay, so I'm just taking the population standard deviation and dividing it down by the square of the sample size? Yep, that's what you're doing. And that helps you to decide. And that's how things are done, because it makes sense to do samples to ensure that a normal analysis can be done. So I could go through an example here. I think you've got an example like this in your homework, so I don't think that I'll spend any more time going through this. But suppose the mean time for an oil change at a 10-minute oil change is 11.4 with a standard deviation of 3.2. That means the population is 11.4 with a standard deviation of 3.2. Well, what if you collect 35 oil changes? Knowing that your sample size is 35, you know that you're going to divide down this standard deviation by the square root of 35, roughly 6, right? So you're going to take this and divide it by the square root of 35, and then you're going to do your normal analysis. And by the way, in your homework, they ask you to explain or describe the sampling distribution. To describe, that simply means explain why or why not it is normal, and give the mean and standard deviation. Why is this going to be normal? How do we know it's going to be normal? I don't know anything about oil changes. Well, I know it's going to be normal because we've got more than 30. So the mean is going to be 11.4, and the standard deviation is going to be 3.2 divided by the square root of 35. And the rest of that you can go from there. Next section, 8.2, you'll have to load another video to find out what happens in section 8.2.